So now we're going to see how to implement those concepts we saw in theory in the previous lecture. And we're also going to take a look at Tensorboard. This is an interface tool that makes it easier to look at the computation graphs and follow the training of our networks. So we're going to start with a brief introduction to graph mode in TensorFlow, and then using Tensorboard to look at the computational graph and also to follow the training. We're going to look at some practical issues about numerical stability and some ways of using those loss functions that we talked about in the previous lecture. And then I'm going to detail more the exercises you're going to do for today and the next few days. These are several exercises. I don't think you can do everything in 2 hours, but you can think of them as work for doing during these short vacations. So we're going to do binary classification in the first example, and then the exercises will also be for regression and multi-class classification. Regression will be to try to predict the mileage, the gas consumption of automobiles based on their features, and multi-class classification will be using the MNIST dataset to try to assign each handwritten digit to one of 10 classes for the 10 different algorithms. So let's start with the Tensorboard. This is a set of visualization tools that you can use to look at your models, visualize, follow learning, and so on. You can see a lot more detail here on the documentation. We're going to just look at this briefly to give you a quick introduction. So in your code, what you should do is to create a logging directory that uses a different folder for each run of the model. Because the way Tensorboard works is that you can select, it will look inside a logs folder for different folders having the logs of different runs. So if you do it this way, if you have a set of subfolders inside the logs folder, you can easily select which ones to plot, and then you can see the graphs. If you put everything in the same folder, then Tensorboard will interpret it as being one single run, and that will be very confusing because you'll have always all the plots drawn superimposed in the same color and so on, and it will be confusing. So one way of doing this is you can import this datetime class from the datetime module in Python, and you create a string with the year, month, day, hour, minute, and second, so that each time you run, you have a different timestamp here. And then inside this root directory, so this logs directory will be the one you'll give to Tensorboard so that it can find all your logs. But inside of this one, you can create different subfolders with different names for each of the runs you're going to do. So if you use something like this, you guarantee that all your logs are in different folders. So now let's start with just outputting to Tensorboard the computation graph. So we're going to use the logistic regression example we saw last time. So basically we are using one sigmoid activation on one neuron, and we are using the logistic loss to model a logistic regression with a single neuron. We are going to do this a bit differently. Remember, last time we had some conversions here because we wanted to allow using NumPy arrays into these functions, and then we converted to tensors. In this case, we're going to assume everything are tensors because we want to use these functions to create a computational graph in TensorFlow, and it's best if everything is a tensor in the whole graph. So prediction receives the features as a tensor. It computes the output of the neuron, and here note this reshape that I'm using, because when we use the matrix multiplication between the features and the weights and then apply the sigmoid, the output would be a matrix with a single column. If we want the labels to be just a vector and not a matrix, then we should reshape this into a single dimension. And this -1 just indicates that for TensorFlow to put there as many elements as necessary to put everything into that dimension. So we are converting this single column into just one vector. Now we can also compute the logistic loss. So this is basically the product of the label and the prediction, and 1 minus the label times 1 minus the prediction, and so the logarithm of the prediction. And we average everything, take the negative of that, and this is our cost. Remember that this must be set up so that we can do batches of examples. So we are not receiving just one label and one prediction. We can have here the predictions for several examples and the labels for several examples. Okay, so now we can compute the gradients. Remember the gradient tape. We have our weights and our biases here as global variables. So we use the gradient tape class to backtrace all the operations we were using, but this time using the derivatives and computing the derivative of the loss function, which is the tensor we are giving here, with respect to the variables that we want. So this is what we did last week. The only change is that now we are assuming that everything comes already as tensors. We are not having any arguments as NumPy arrays that we need to convert. And now we're going to create the computation graph using the autograph functions here in TensorFlow. So this is basically tracking all the computations we are doing and building the graph of tensors and operations. So those graphs that I showed you last week, they were drawn using Tensorboard, and now we're going to see how to do that. So this autograph is implemented in TensorFlow in this function here, called function. So this is a wrapper. We can use this decorator in Python to wrap any function that we want into this one. And what this does is to trace all the code that is going to be executed and use that to create the graph. So what we can do here is, for example, use this decorator on the create graph function and call the prediction function, so that the computation graph we're going to create will be this one here, will correspond to this part. And to write this to the log, we need to create a summary writer. So you can use from this summary module create file writer and indicate the root folder for all your logs. No, sorry, the actual folder for this particular log. So in this case, it's inside the root folder, and it has one specific unique name, so that each time we run, this gets logged to a different folder. So we create a writer for this, and this is the one we're going to use to write all the logs. And now the write graph function, which is this one here, will turn on tracing so that we can follow the graph. And then we're going to call the create graph function. The create graph function receives the x and y. In this case, it only needs the x, but we're going to see later on when we complicate a bit the graph. But it receives as arguments the features and the labels, and then writes the trace, so the graph of the computations, to the log. Okay, so if we do it this way, we need to load the data first in order to create, to run the prediction, but we're going to do this like we did last week. We're going to load the data. The labels are here in the last column, the features are the other columns, and we're going to standardize everything and just write the graph. So if we do this, we have in the Tensorboard the graph for our computation, in this case only for the prediction. There are two reasons for doing this. One, which is the one we're going to use here, is just to look at the model in that representation. So we're going to create a graph to export to Tensorboard and look at it. Another reason for using autograph and creating the whole computation graph is to optimize execution. Because if you create the whole graph first and then run it, TensorFlow can better assign different parts of your computation to the GPU, to the CPU, or even distribute in the GPU in different ways. So it's a good idea when you want more performance to create the computation graph first and then execute it. We will not look at that in detail because for one thing, that performance is not a very an important part of this course, but especially because when we start using Keras, we will not be have to worry about this because Keras does this internally, and so we don't need to know all these details and code everything by hand. So basically, we're just going to use this autograph functionality of TensorFlow to represent the graph on Tensorboard in this session. So after you save the logs, you run Tensorboard. Tensorboard is a HTTP server that will run locally. So you run Tensorboard with the logdir parameter here, where you specify the root dir for your logs. So in this case, it would be this logs folder here. This tells Tensorboard where to find all the different folders with the different runs. And then you just open your browser and set it to the local, to the home address and this port, 6006. This is easy to remember because it looks like Google, visually it looks like Google, and you can remember that easily. And at this port you can find Tensorboard, and you'll see this kind of interface that I showed here, where you can select the graph, the different plots, and so on. So this is the graph that we created in our prediction. If you note here, our prediction does matrix multiplication of the inputs and the weights, gives it this name, adds this up and gives it this name, net, and then does a sigmoid activation with the name output, and then reshapes it. So when we look at the graph that we have here, we have the matrix multiplication, then everything is added, and this is, we called it net. So this was a default name that TensorFlow gave. This was the name we gave. Then the sigmoid activation we called output, and then we have the reshape operation there. And this is the computation graph that we have here for the prediction. We also have this other tensor that we never used, that we didn't use yet, the labels, but this is the computation graph that we created. We can include the loss function too. So instead of just calling prediction in our create graph function, we can store the result of prediction and then call the logistic loss on the prediction and the labels. Now we do the same thing. We create the writer, we write with the trace on to the log and so on. But now we get this more complicated computation graph, where we have here the output of our neuron, so multiplication, the sum, the sigmoid activation, then the reshape, and then the different branches here in the loss function that we are computing, and then computing the mean and so on. So you have here in this graph the whole computation from the prediction and the loss function. But we can go one step further. Let's create the whole graph, including the gradient information. So you can see the grad function already calls the prediction, calls the loss function, but does this inside the scope of the gradient tape so that it can then trace all the computations and compute all the derivatives for the stochastic gradient descent that we're going to use for training. So if in the create graph function we call the grad function like this, this autograph from TensorFlow will track all these computations, including the ones done by gradient tape, and will put them all in the graph. So in the graph we will have the same thing as previous, all these computations, but these will also be connected to the gradient computation. So these are all the derivatives that gradient tape created in order to allow us to compute the derivatives with respect to the weights and the biases there. So this is the complete computation graph that we have for training our network. We can also add values to TensorBoard. We also need, when we write things in the logs, to give one step argument there. In this case it was 0 because this was just to export the graph. But you can use this step argument to indicate the x value for plotting anything. So in this case we're going to do the set of epochs, 50 epochs in training, and we're going to use the current epoch as the step for plotting the training loss. And the way we do this in the TensorBoard is we do the training as before. We shuffle our data in each epoch. We take a batch from the features and from the labels. Note that in this case we are already converting everything to TensorFlow tensors, because we don't want to send NumPy arrays into our computation graph. And we do that by first typecasting our NumPy arrays as float32. This is best for if you're using GPU and so on, it's more efficient. And then we convert that into a tensor with the constant there. So we do this for the features and the labels. We obtain the gradients. We apply the gradients to our optimizer, the same thing as you did last week. And now we compute the prediction for the whole data set, and we compute the loss function. Okay, I forgot this part here. There's a typo here. We also need to convert this to a TensorFlow constant, but you get the idea. And now we have the loss function. We can print it out on the console, but we can also send it to the logger to log it into that TensorBoard log. So we log a scalar value, which is the loss function for this epoch, and we give it a correspondent x value, which is the epoch. So this allows us then in TensorBoard to look at the training values, and we can see the loss function is going down for training, and then we start having here some problems where we start getting not a number. So some values disappeared there because there was some kind of overflow, and we don't have actual numbers there. So if we look at the console, at the print, we can see this. We can see the loss function there reducing, and then we see sometimes not a number appearing. So the reason this happens in this case, it's because of the stability of this logistic loss function. We are computing the logarithm of the sigmoid activation. So the logarithm function, which is here in blue, as the x value tends to 0, the logarithm will tend to minus infinity. And we cannot compute the logarithm of negative numbers or 0. The sigmoid function will never reach 0. It will approach 0 with very, very small numbers. And when we do this, the logarithm of the sigmoid, we should get a function that is approximately like this. It tends to go linearly here towards minus infinity, so it should be well behaved. But we have this problem here. We have very, very, very small numbers here that are not quite 0. And then we put that as an input to the logarithm. And so we have very small numbers here that should go on this region, but never, since these very small numbers are never 0, they should not give us problems. Of course, when we have rounding errors in given the precision that we're using or something like that, then this will be a problem with the stability, the numerical stability of this function, and that's why we get this not a number occasionally. So we need to compute the logistic loss, but we cannot compute it in this naive way. Otherwise, we risk having these problems. There are several solutions for this. This is an example. We can take, if the input, so we are trying to compute the logarithm of the sigmoid function. And for the logarithm of the sigmoid, if x is very small, we can just take it as x, because it will be this linear part here if x is very negative. Otherwise, we can take the x minus the e raised to x, or the logarithm of 1 plus x of e raised to minus x, and so on. We take this in different stages. Or in the case of TensorFlow, it uses this formula here, where y is the label that we're trying to adjust our model to. X is the input to the sigmoid function, so it's not the prediction, but the net sum of the weights and the inputs for our neuron before applying the sigmoid function. And so this way of computing this is more stable. We can do this by using the sigmoid cross entropy with logits from TensorFlow, which does this computation in this way, that allows us to compute that logistic loss without numerical instability. But to do this, we need to provide not the output of the neuron, which is the sigmoid applied to that weighted sum of the inputs, but just the weighted sum of the inputs, because then the sigmoid cross entropy with logits function will aggregate both computations, the sigmoid and the logarithm, in order to compute this in a more stable way. And that's why it's called with logit. So basically the logit is this part that we are calling net here, which is what enters into the sigmoid function, activation function. Okay, so we need to modify our code a bit. We're going to keep the prediction. The prediction outputs the sigmoid activation, but we're also going to create another function that is this logits that just does this part. So it does everything our neuron was doing without the sigmoid activation, and then also reshapes it and outputs just the sum of the products of the inputs and the weights. And now, to compute the logistic loss, we're going to get the logits from that function, and instead of implementing ourselves the function which gives us these problems, we're going to use the sigmoid cross entropy with logits from the TensorFlow. So it's here in this neural network module. You can get the function there. We just input the labels and the logits for the prediction, so before the sigmoid activation function, and it will give us a vector with all the sigmoid cross entropy, and then we compute the mean for that and return that. So now we can experiment, run our code. Remember that now we need to change here also, because we don't want to compute this by hand also when looking at the loss for each epoch, but we just call the logistic loss function that we created here, and it takes care of everything. Also, the gradient can now be simplified because we don't need to compute the prediction first. We just call this logistic loss, which in turn will call the logits function. Okay, so now this works. We don't have problems with stability. So this is important in practice. It's often the case that these functions are not trivial to compute in a stable way when you are dealing with finite precision in your numbers. So for functions like the mean squared error, you can use this mean squared error loss function here, or you can implement your own. So you can use this from the losses, I think this may be deprecated already or close to, because some of these were moved to Keras, but you can use them also from the this neural networks module. You can find these ones there. But in any case, for the mean squared error is not a problem, because mean squared error has no stability issues. But for the sigmoid and the softmax cross entropy, use the functions available in TensorFlow. Otherwise, you risk having these kinds of issues and getting those overflow problems. So let's see an example of computing a regression with a multi-layer perceptron. We're going to use this auto miles per gallon data set. These are available at the UCI repository. I give you a modification of this data set just to make it simpler to load the data. And what you should do is to load the data, shuffle everything before splitting into training and validation. These are 392 examples, so we'll use 300 for training and 92 for validation. The target value is the first column, which is the miles per gallon. This is how many miles the car can travel with 1 gallon of fuel, and gives you an idea of the consumption of the car. And we're going to standardize all the features and the target value. So standardizing the features is important because the features are in different scales. And since we are training the whole network with the same learning rate and so on, we don't want some features to have more weight than others just because they are in different scales. It's also important for numerical stability, and if we center everything at 0, the network, it makes it easier for the network to learn. So when we standardize, we are putting everything with an average of 0 and a standard deviation of 1, and that will make it easier for the network. Standardizing the output is also useful, not only for centering everything, so you don't force the output neuron to have to aim at some values away from 0, but it also can help you minimize numerical problems depending on the scale that you're working with on the output, and it can help you have a more standard approach to looking at the errors and looking at how the network is training and so on. Because with different regression problems, if you're working in millimeters or in kilometers and so on, you can have very different scales, and it can make things a bit confusing. So in classification, it makes no sense to standardize the output because those are just class labels. But in regression, it can be useful to standardize the output and avoid some of these problems. However, remember that you need to store or keep all these rescaling factors that you use to standardize the features and the output, so that when you apply your model in a real scenario, you can convert everything from your original units to the model and then back again to the original units. So use a linear output for the last neuron. It's only one neuron. We're only predicting one value here. And since it's a continuous value, we don't want any activation function to restrict the output of this neuron. We use the mean squared error loss function. So the probabilities model here is that the true value is centered on our prediction plus or minus some random error that we have. So we using that probabilities model, the maximum likelihood solution is the minimization of the quadratic error. And then you can try different architectures, different activations on the hidden layers, different learning parameters and so on, and experiment a bit with this. So just to look a bit at the details to get you started, we're going to load this TSV file. We're going to split the data into validation, so everything after 300, and training. But before we do that, we shuffle the data so that in the case the cars are sorted by year or something like that, we don't have a biased split between training and validation. We are going to standardize, and we're going to keep all the standard deviations and the means so that we can go back and forth between the units we are using in the model and the units in the data set. Then you can, to create a model, it's easy. it makes it easier if you create some functions to create the network. So here I created a function for generating a layer of neurons. I tell here I give a NumPy array with the inputs for this layer and a number of neurons that I want. So what I need is to create a TensorFlow tensor, a variable that is initialized at random and has as many rows as the columns in the inputs. So the inputs would be, for example, the features or a batch of examples where the columns are the different features. So if the columns are the features, this must correspond to the weights of each neuron. And we are going to put the neurons in columns. Remember what we saw last week. So the number of weights of each neuron is the number of features in each example, and it will be the number of rows in this matrix. The number of columns in this matrix of the weights for this layer will be the number of neurons. So these are the weights, and the bias is just an array with as many values as the neurons we have in this layer. So now we return the two tensors, the weights and the bias, having created the layer. To create the network, we can receive a list with the number of neurons for each layer and a NumPy array showing us how the inputs are shaped, so how our X values are shaped. We're going to start with these empty lists, but we're going to start from the matrix with the examples, the input data, and we're going to create a layer using this input data as input and the number of neurons in the first element of this list. So we can use something like this. Let's say it's 25, so 25 will be the number of neurons on the first layer. We create this layer. We append this layer to our network. So our network will be a list of tuples with the weights and bias for each layer. And we can also create just a flattened out list with all the variables. So we're going to extend this list with the weights and the bias. And so we have that list of variables that we can use for the gradient tape and for the stochastic gradient descent and so on. And now we're going to point the previous output not to the input values, but to the output of the previous layer. So basically it has the shape of the weights that we have in the previous layer. And now we're going to create the next layer and so on. And this way everything will match correctly because we are using the output of one layer as the input of the next and using the appropriate shapes for all of these matrices. Okay, so now we can create a network where we have a list of tuples for all the layers, each one with the weights and the bias, and a list with all the variables we have in our model. This is useful for training the model. So you can start with this kind of functions. You can create your own or use these in order to make it easy to create your models. Now we can, for example, save the graph with the model. We can create this prediction function. For this particular problem of regression, what we're going to do is, given a batch of examples, we're going to start from that as an input. We're going to go through our network. Remember that this network is a global variable with all the tensors we need for our model. We're going to start on the first layer, multiply the input by the weights of this first layer, add the bias value, and then apply the leaky ReLU activation for this layer. And now we are going to replace this net. So this net was began by pointing at the input array, but now it's pointing at the output of the first layer. So that when we go to the second layer, we are now multiplying the output of the first layer by the weights of the second layer and so on, and applying the leaky ReLU activation. And we move on until we reach the layer, the one before last layer, not the last layer, but the one before that. Because the last layer is different. We're going to just do the multiplication of the net of the previous layer and the weights of the last layer, add the bias, and then output just that value after reshaping it, just to have it in a vector. Because we do not want to apply the activation function, the leaky ReLU, to the last layer. In fact, in this case, since it's a regression, we do not apply any activation function to the last neuron. So if you want to write this graph, you can just, for example, call predict. We don't need all the derivatives and so on. We just need to look at the model of our network. So if you create the graph calling this predict function, you get something like this. In this case, I created 3 layers with 25, 15, and 1 neuron, and we have them here, the matrix multiplication, the sum, and then the matrix multiplication, the sum, and so on. And then we have everything until we reach the end. If you want to simplify your graph, you can add names. You can create a name for a block of operations. And you can do that with this name scope here from TensorFlow. So in predict, when we are doing these operations of adding, of multiplying the matrices, adding, and then applying the activation, we can just call this layer with some number, layer 1, layer 2, and so on, and do these operations within the scope of that name. The reason for doing this, it doesn't affect the computation itself, but it makes the graph prettier. So you have this layer 1, layer 2, and the output. And if you want, you can go on Tensorboard and double click on one of these and see what's inside. So you can see inside these operations, but if you just look at the graph like this, they are grouped in those blocks, and it's easier to see the architecture of your model. Okay, so try with different parameters here for the stochastic gradient descent, the batch size, the architecture of the network. You may have some problem with not a number again. In this case, it's not the loss function. The loss function is the mean squared error. You can implement it and so on. I don't show it here, but this will be part of the exercise. But the problem here is that if we have many neurons, then even this original initialization using a normal distribution, this normal distribution by default has a standard deviation of 1, can give you weights that are large enough so that when you have lots of neurons and with a rectified linear unit activation, which doesn't cap at 1, it can be larger, you can start having inputs that are very large, and then you can have overflow problems in your network. So you can solve this in this case by shrinking the size of the weights when you initialize them. For example, use as a standard deviation 1 divided by the number of neurons in that layer. This is a good heuristic. It works at least most of the time in this particular case. There are more sophisticated methods of initializing weights. They generally use this kind of reasoning, looking at the number of neurons in one layer, in the next layer, and so on. But we're going to look at this in more detail next week when we start using Keras, because we're not going to implement all of these by hand. So it's more useful to look at the theory behind this when we start using these functions already implemented in the API. But in this case, if you have problems with not a number, try this, initializing with smaller values, and also check for common mistakes. For example, I reshaped the output of the prediction here so that the output is a vector, because I loaded the labels as vectors. This is the first column of the matrix. And also for the loss function, I will assume that everything is a vector. But if you forget reshapes and if you have things in different shapes, you will probably get problems with the loss function. So check your code if you start having problems. Look at how things are going in Tensorboard. It's easy to follow the graph and so on. So when you look at the errors, you can also convert back into miles per gallon. Note that since we standardized everything, our loss function, which is the quadratic error, is being measured on this arbitrary scale centered at 0 and with a standard deviation of 1 after standardizing the values. If we want to convert this quadratic error into miles per gallon so that we have an idea of what our function is, our predictions are diverging from the real values, we need to take the square root of the quadratic error because that one is squared, and then we need to multiply by the original standard deviation. We divided by this one to standardize, but now we multiply by this one to get the error in the same scale. So if you want, you can output when you are tracing your the performance of your model, you can convert this into miles per gallon so that you have an idea of what the error is in the original units of the problem. And you can then write this to the logs, for example, with different labels, so that then you can see them in the plots in Tensorboard. Okay, another exercise that you're going to do is to use solve a multi-class classification problem with MNIST. The MNIST dataset is a set of images of 28 by 28 grayscale pixels with handwritten digits. This is a dataset that is available in Keras, in TensorFlow. So to load the dataset, you just need to import Keras and then get the MNIST dataset here. So you just call load data, and it will give you a tuple of tuples. So one is the test images and labels here. These are 10,000 that you can use for testing, and 60,000 images here and labels in the first tuple that you can use for training and validation. So what we need to do is to reshape these images from 28 by 28 to 784 features so that we can have our data set as a single two-dimensional array where each row is one example, one feature, one image, all in the rows, and then all the images in different rows. And this training set of 60,000 images, we're going to split 50,000 for training, 10,000 for validation. So you can use, again, these functions that we saw here for the miles per gallon problem. The thing is that now you need to change a bit the predictions, the outputs, the log hits, and so on when you try to fit this into the softmax cross entropy function. But I'll leave you to think about that to solve that problem in the exercise. Some things that you need to know is that we're going to use the softmax output to give us the probability of each class. So in one example, we'll have the probability of being a 0, the probability of being a 1, a 2, 3, 4, 5, and so on. And so we're going to encode the labels to train our network in a similar way. These original labels that we have here are just integers between 0 and 9 to indicate which is the label for the digit. But you can use this function here from Keras utils to categorical, which converts these integers into this one-hot encoding. So since there are 10 different labels, each example will be an array of 10 values. All of them will be 0 except the one corresponding to the actual label for that example, and this one will be 1. And this is what we're going to try to approximate with the softmax activation, so that if we are looking at a 5, for example, the output of our network should be close to 0 on everything except the 5, and close to 1 on the correct label for that. So we need to use labels with this one-hot encoding, so you can use the two-categorical function from Keras. If you want to look at the output of your network and convert that, because the output of your network for each example will be a vector like this, with the probabilities. If you want to convert that into a specific label, you can use the argmax from NumPy if you want to check the labels, so that you get the position corresponding to the maximum value, and this will be the corresponding label, since the labels here are just numbers from 0 to 9. Okay, so you're going to have to create your function, your network. You're going to have to use the appropriate output of your network. So this will be a softmax using 10 neurons as the output. Remember that we have 10 classes here, so you need 10 output neurons and apply the softmax on them. But the loss function, because of the numerical stability, you should use the loss functions from TensorFlow for the softmax cross entropy. You can use the one softmax cross entropy with log-its, so that one will need to receive the log-its, and this means you'll have to do a similar trick to what we did before, create a prediction function for predicting the class using your network, but also create another one that just outputs the log-its, so that you can send it to the loss function when training. So you can try different dimensions, different parameters for optimization and so on. You can check for overfitting. So the idea here is that you leave this test set just at the end to estimate the true error if you want. But with the training set, you're going to split it into training and validation, and you can follow the validation error during the training of your network, so that you can check if your network is overfitting. That is, if the training error is much lower than the validation error. So this can help you choose the best architecture, choosing different sets, different numbers of layers, different numbers of neurons per layer, and so on. Remember the shapes of the tensors. So in this case, you should not reshape everything into a vector when you do the predictions, because your predictions must be a matrix. They must be a matrix of this shape, and the labels you are comparing to must also be one-hot encoded, so they will have this shape. So this is not just applying the same recipe we saw before. You need to think a bit about the shapes of the tensors that you're using. If you want, you can then check this web page that has the accuracies for different models. So basically, this works better if you use convolution networks. We're going to start looking at those next week, but you can experiment with your own multi-layer perceptron to see how well you can do in this simple data set. Okay, so that's it for now. You're going to start doing these exercises in the tutorial. Remember that because of the vacations, we are joining the two tutorial classes, P1 and P2, today, but then we will check the Hangouts during the week. If you have questions, we can help out a bit. So for today, start with the binary classifications, using the gene data with one sigmoid neuron, and then also you can apply that to the banknotes data set. So this is basically what I showed you in more detail during the lecture, and you have in the lecture notes. Then you're going to solve the regression problem of those miles per gallon and the multi-class classification with the MNIST dataset. And basically, this covers the three types of activation functions for the output and loss functions that we've been looking at in this lecture. Okay, so that's it for now. I'm going to log into Zoom and we can talk a bit if you have any questions. See you soon.